Okay, so a compound event is like flipping a coin. Okay, so you do it once, you got 1 out of 2 chance of being a heads. Do it again, you got 1 out of 2 chance of being a heads. So the chance of getting a heads both times is 1 out of 4. And you can see out of these 4, the only one that has heads both times is the top one. So 1 out of the 4. So doing it this way or doing it this way, you get the same answer. And flipping a coin is independent events because when you flip it the first time and then you reflip it the second time, the first one does not affect the second one. Let's look at another example of independent events. So this will be independent. An independent event is I'm going to draw a card. What's the probability of drawing a heart, putting it back, and drawing a heart again? Okay? How many cards are there in a deck of cards? 52. How many hearts are there? 13. You got a 13 out of 52 or 1 out of 4 chance of drawing a heart. Then if you put it back in the deck, shuffle it up the deck, and draw it out again, what's the chance of drawing out another heart? 13 out of 52 or 1/4. So the probability of drawing a heart back to back is a 1 out of 16 chance if you put the card back in. That's independent events. The next one we talk about is dependent events, how the occurrence of one affects another. So we're going to do that with a dependent. What's the probability of drawing a heart, not putting it back, and drawing a heart again? Okay, so this time you're not going to put the card back in. So you got a 13 out of 52 chance or a 1 out of 4 chance of drawing a heart the first time. That doesn't change. But the second time, if you don't put it back in, how many hearts are left? 12. How many cards are left? 51. Now, 12 over 51 reduces down, so it's 1/4. 12 over 51, 3 goes into each. So this is 4 and 17, I think, right? So you got a 4 out of 17 chance the 4s go into each other. So you got a 1 out of 17 chance of drawing hearts back to back if you don't put the card back in. Okay? Now, let's do that for aces. The probability of drawing an ace and don't replace, and probability of drawing an ace again. What's the probability of drawing the first ace? 4 out of 52, which is 1 out of 13. Then how many aces are left? 3 out of 51 or 1 out of 17. So probability of drawing an ace and then drawing another ace is 1 out of whatever 13 times 17 is. One out of 221 chance of getting an ace and an ace. Okay? So that's dependent events. Okay. Mutually exclusive events are events that cannot happen at the same time. Okay? Cannot happen at the same time. So, going back to our cards. You draw a card. What's the probability that's either a 9 or a 5? Well, can a 9 and a 5 be on the same card? No, they're different cards. So the probability of drawing a 9 is 1 out of 13. Or means we add them. Probability of drawing a 5 is a 1 out of 13 chance. Okay, because there's 4 out of the 52. If we add them up, we got a 2 out of 13 chance of drawing either a 9 or a 5 out of a deck of cards. Okay, a 2 out of 13 chance. Those are mutually exclusive, things that can happen at the same time. You'll see the word or in there, and so you add them. Now, overlapping events are like mutually exclusive, but they have something in common. So it's an or, but you're counting something twice. Let's go back to cards again, because I know cards. Okay? I grew up playing cards. In the wintertime, back in the day when I grew up, guess how many TV channels I had? Three TV channels. And one of them was PBS, so we never watched that one. So it was CBS, and for a while I was growing up, it was ABC, it was NBC, and then it changed to ABC. They changed kind of stations around. But I had basically 2 networks to watch. So that's all I had. There was no cell phones. There was a farm that we had to do stuff on, but in the middle of winter, we played a lot of cards. So when I talk about cards, that's because we played a lot of cards growing up because there wasn't really that much else to do. We lived 13 miles out of town. And we just didn't go to town just for hanging out. So played a lot of cards. So a mutually exclusive event is the probability of drawing a 9 or a red card. This might be one that you see a little later. The probability of drawing a 9 or a red. What's the probability of drawing a 9? 1 out of 13, because there's 4 out of the 50. I'm going to write them out of 52 for right now, so you maybe can see this a little bit better. You got a 4 out of 52 chance of drawing a 9. Then, what's the probability of drawing a red card? 26 out of the 52. Now, if you think about all the cards, how many red 9s are here? 2 of them. How many of these are red 9s? They're the same red 9s, right? So if I add them up here, I've counted them twice. So it's like counting 4 red 9s. Are there 4 red 9s in a deck? No, there's just 2 of them. So we have to subtract 2 of them because we double counted them. So if you have a situation like this, where you're counting the same thing twice, you count the one thing, all of the one thing, all of the other thing, and subtract the ones that you're actually looking for to get the right number. If it's an or statement, if it's an and, then that totally throws it out. That's something totally different. But if it's an or, then you got to go through this. 4 plus 26 is 30, minus 2 is 28. 28 out of 52, divide them both by 4, 7/13. You got a 7 out of 13 chance of drawing a 9 or a red. Okay, Vegas was built on this stuff. Okay, Vegas makes billions and billions of dollars every year on knowing probabilities. And they rig their games on probabilities. They want to win at least, 35% of the time. No, more than they want to have the players win at least 35% of the time. Okay? So they got to rig all their games to make sure they win 65% of the time and the players win 35% of the time, because if the players don't win at all, then they'll never come back. So you got to give the players enough enticement to come back. Ooh, I could win. But in the end, you're making a lot of money. Okay, so it's all numbers, it's all probability. Okay, so if you ever build a casino in Vegas sometime later in life, or you work in a casino in Vegas, it's all built on numbers and probabilities and all this stuff. And they got really smart math people working out the numbers so they make money. Okay? Now, every once in a while, people con them out of a lot of money because they figured out their tricks. But yeah, that's another story. But, okay, A and B are mutually exclusive. If you have mutually exclusive, you have the word or. When you see the word or, you want to add. What's 59 plus 22? 81%. 0.4 plus 0.3 is 0.7. When you see the word or, you add. Okay? You toss a coin again. Is that independent events or dependent events? Does what happened the first time matter for the second time? No. So it's independent. Now, drawing a card and not putting it back and drawing a card again, that's a dependent event. This is an independent event, but these are independent events, but it's a compound event. Okay? So you take the probability of this one and the probability of the other one, and you multiply them together. If you see and, you got to think multiply. Okay, for this one, the spinner lands on an even number. What's the probability of landing on an even number? 50%, 1 out of 2. What's the probability that if you choose a tile that are numbered 1 through 10, it'll be even? 1 out of 2, 50%. What's 1 out of 2 times 1 out of 2? 1 out of 4. Probability is 1 out of 4 that you'll hit an even number of both. Envelopes. I have 1 red, 2 blue, 3 green, 6 yellow, or 3 green, 3 yellow. How many total envelopes are there? 9 total envelopes. What's the probability of blue or a green? Well, blue envelopes is 2 out of 9. Green envelopes is 3 out of 9. Since it's an or, you get 5 out of 9. All right, cards. What's the probability a card is a 9 or a red? We already did this. Okay, so the probability of a 9 or a red is 7/13 because it's 26 over 52. That's the red card. The 9 is 4 out of 52 minus the 2 that we counted twice is 28 out of 52, which is 7 out of 30, or 17 out of, no, 7 out of 13. There we go. All right. Here's like the cards, but it's with professors. So I'll make a little box. Professors and teaching assistants. So if we do professors in the top row, if we have a male professor and a female professor, there are 6 male professors, 10 female professors. There teaching assistants, there's male teaching assistants and female teaching assistants. So there's 12 male teaching assistants and 8 female teaching assistants. So what's a probability that you'll either have a professor or a male? Well, the professors, there's 6 male professors plus 10 female professors, which are 16 professors. And then males, well, there are 6 male professors and okay, how did I do this? 12 male teaching assistants. I think my graph is off. Let's not look at this. Let's just look at this. 12 male teaching assistants. So out of the males, there's 18 males. So you take 16 professors plus 18 males, and you get 34. Well, how many total people are there? Well, there's 6 and 10, and then 12 and 8. So there's 20 plus 16. There's 36 total people. Well, if you do this, that's 34 of the 36 that are both males and or professors, which is too many. Okay? What you have to do is subtract off the what? Male professors. Well, there's 6 male professors. So take 16 plus 18 minus 6 is 28 out of the 36 are male or professor. If you divide them both by 4, you get 7/9. 7/9, you have a 7 out of 9 chance of getting a male or a professor. Okay? So takes a little bit more for that one because you got to think your way through it. Lastly, whoa, come on, flip. There we go. 8 from the total.
8 minus 36 is equal to 28.
But why, oh, the 8 female teaching assistants? Is that where you got the 8? The ones that don't belong at all? You could probably do that too on this one. For this one, in math class, 85% of the students have been to the ocean. 55 have been to the mountains, or 85% of the students have visited the ocean, 55% have visited the mountains. Then 50% said they've been to both. Okay? How many have been to the oceans or the mountains? Well, you take the ones that have went to the mountains plus the ones that have been to the ocean. What's 85 plus 55? Like 140, right? Can you have 140% of the students? No, because you count some of them twice. Minus the probability that I've been to both of them, minus 50. So 90% have either been to the mountains or the ocean. Okay? All right. So what I'm going to do is I'm going to throw out today's assignment, and I'm also going to throw out yesterday's assignment, which is tomorrow's assignment, if you catch my drift. And so you got that, and then Monday we'll review for the test, review for the quiz, take a sample quiz, and then Tuesday we'll take the quiz, and then Wednesday, Thursday, next week finish up the chapter.